All right. Hey, everyone. Thanks for joining. My name is Ali Blasi, and I'll be your host today as we walk through how solar storms are affecting drilling surveys and hitting your target, a topic that many, myself included, thought was only relevant to Alaska, Canada, Norway. But if you're around on May 10th, you know that's not true. So I've got Mark and Paul here with me today to talk through this. So will you guys introduce yourselves?
Sure. Thanks, Ali. Thanks for having me. So my name is Marc Willerth. I've been in wellbore positioning and varying facets for about 15 years. Most recently, I was a senior technical advisor with Magvar, who provides magnetic modeling, survey correction, and wellbore placement services. And then several years ago, we were acquired by Helmerich and Payne, and so I've stayed on in a research and wellbore placement advisory role since then.
Yeah, thank you, Ali. I appreciate you having us. So my name is Paul Perrion. I am the technical sales advisor for survey management with Helmerich and Payne. I've been in the wellbore positioning field for about 16 years. Previously with the direction company, now I'm with Magvar, now H&P Survey Management. So yeah, I'm looking forward to getting through this.
Well, thank you. We'll jump right in. I never like podcasts or webinars that have long introductions. We want to get to the meat. So something easy. Tell me what's happening. What's going on?
So I'm going to share my screen and I'm going to show you what happened on May 10th. So on May 10th, or May 8th, actually, there was a solar flare. And I don't know if you can see the cursor, but I'm circling it right here. And that produced a coronal mass ejection, which was directed towards Earth. And what that did, it was caused magnetic interference with the Earth's magnetic field. And it caused significant issues with surveying all around the world, really. Typically, like you said earlier, Ali, this does affect the northern latitudes, like the Alaskas and the Canadas. But in this case, it was such a strong event that we actually had issues or interference all the way down into the Permian Basin. We saw auroras all the way down into North Carolina. So this is a family member of mine who sent me some pictures. And we saw auroras all the way down into North Carolina, which is pretty rare. It is beautiful. It is very good to look at. It's a beautiful thing to look at. But if people knew in a drilling aspect how much this can affect your survey accuracy, you wouldn't think it was as beautiful. So yeah, so that's pretty much the story of what happened during the May 8th, May 10th, and it lasted all the way until May 13th, which is an unusual length for a solar event. 2-3 days is unusual. Typically, they last very short, although there are times where it can last, 2 or 3 days or even up to 2 or 3 weeks.
I think you guys had described this earlier when we were talking as a magnetic hurricane season. And for those in Houston recently, there was, the hurricane that came through. What did you guys mean by that analogy?
Yeah. So I can share a graphic here if you want to hand me the screen, Paul. So the solar activity goes through 11-year cycles, and we are on the upswing of the most recent set of these cycles. So in addition to getting stronger magnetic events, so the event back in May is what's called a G5 storm, actually the highest classification of magnetic storms that we have for space weather. And interestingly enough, in line with our theme, a month later in June, there was a G4 storm that hit again. And this is going to continue increasing, throughout the next year or two. And there's even thoughts that it might be more still intense storms on the downswing of this cycle. So just like you were saying, Ali, just like we know going from June into July to August, the Gulf is heating up and you're going to get more tropical storm activity, we're going to get more magnetic storm activity over the next few years, and that's going to be impacting our surveying operations.
Okay. And you had talked a little bit about the Earth's magnetic field, how it's powered by the planet's rotation. Can you go into a little more depth there too on what the actual causes behind what's happening?
Sure. So the Earth has a molten iron core and rotates, and that makes the Earth act like a big magnet. And that magnetic field actually protects us from the solar flares like Paul was talking about. So the sun emits a lot of energy, and it's almost like a force field around our planet. And the fact that it's caused by the Earth's rotation, that magnetic field's actually aligned with the Earth, and that's why you can use a magnetic compass. Like, that's actually why magnetic north exists as a thing. But when you have this external interference and you have these solar storms hitting it, that can shift the direction of the field while it's reacting to this stimulus. And when it shifts, that impacts how your magnetic measurements work. It's almost like flying an aircraft in the wind. To keep the analogy going, if you were trying to navigate in an airplane and you flew into a hurricane, you wouldn't trust your equipment the same way anymore.
Mm-hmm. Mm-hmm. No, I totally see that. I think that when we had talked about this previously, you had also mentioned an example with a windshield, and if it's raining, it's
Yes.
being deflected. Yeah, when you walk through that one, I liked that analogy.
Yeah, no, that's again, it's great because the idea is that the windshield keeps rain off you, but if it's getting a lot of rain, you have to pull over. Like at a certain point, you can only clear so much water off the windshield, and it's no longer safe to drive in an intense storm. And a similar thing can happen with these magnetic storms. There are certain times where, even though there's a little bit of activity, it's safe to continue operations, but sometimes the intensity causes unpredictable things to your measurements, and you might just need to stop or take special precautions towards, compensating for this kind of activity.
So with that, how is this impacting drilling operations? At the beginning, we told the audience what it means for hitting your target. Can you guys walk through how this affects drilling operations?
So this could affect drilling operations multiple ways. If there's a solar storm happening, typically your surveys, because they're using magnetic information from the Earth's magnetic field, would be affected, right? So a lot of times what happens in the northern latitudes, the Canadas and Alaskas, they'll stop drilling. So it'll take longer to drill a well. So if there's a solar event, some operators will just decide to stop. There could be collision issues involved, so they just stop drilling. We do have tools in place that we could use to mitigate a solar event. We do need planning ahead of time to know. We have to bring equipment out to the rig to monitor a solar event so we can correct for it. But it could affect that in a way where they would have to stop drilling. If they continue drilling, if they did continue drilling, it could affect their surveys where their accuracy is off. They could be anywhere from 10 feet off or 150 feet off. So that's kind of how it would affect drilling operations.
Yeah, and a visual is here with this graphic. So this is actually the output from a measurement station like Paul was talking about. And I know a lot of the audience is going to be magnetic field experts, but basically these three tracks are three different components of the magnetic field. So the top one is the lateral direction, which is equivalent to azimuth on a survey. So basically, which direction is magnetic north pointing is the first track. The second track is the vertical angle of the field. And the third track is actually just the overall intensity. And when you're surveying a well, you could think of it this way. This top track is what direction do you think you're going? And the bottom two are used as verification for, do I think I have a good measurement? So they're used as a quality control measure. And in this case, there were sustained periods. So this data is from Canada, from Alberta. In this case, there were sustained periods where you had 1 or 2 degree azimuthal errors from the field twisting, but it was not always sure that your quality control criteria would be equally effective. So in some cases, I have this vertical line here that shows you could have a 2.5 degree azimuth error that is not detectable by traditional QC because the field just turned. Again, it's like driving in a windstorm or flying in a windstorm, and it's just pushing you. Unless you actually have instrumentation that's measuring this, there's no way to compensate for it or correct for it. You could stop and wait for the winds to die down, or you would have to actually have additional information supplementing your operations to continue safe drilling.
And I think it's important here in this particular graphic, you see measured azimuth error of 2.5 degrees or, greater than or less than, whatever it is, right? This area, this measured azimuth error, is a 1-to-1 survey error, right? So if you're taking a survey and it's at 90 degrees, your actual survey could be at 92.5 degrees or 87.5 degrees. And every time you take a survey, you're going to have that error. It's going to get bigger as you go. So I think the important part here is it's a 1-to-1 survey error. It's going to grow as you drill. This was a 3-day event. So not all of the surveys were that large, right? Or that error was that large. but it was definitely significant enough to cause substantial survey inaccuracy while drilling.
And to put that in practical terms, a good rule of thumb to have in your mind if you're doing lateral drilling is a 1 degree azimuth error is about 17 feet of horizontal error for every 1,000 feet you drill. So if you drill 2,000 feet overnight, you're now 34 feet off. If you're setting records like some rigs in Texas and drilling 6,000, 8,000 feet in a day, 17 times 8, it adds up.
What is our margin of error that operators give for a window, right? So you're talking huge swings. That seems really outside of the scope.
Yeah, often drilling windows might be, let's say, plus or minus 25 feet. So if you continued on for a few thousand feet under these types of conditions, you might have literally no chance of hitting your drilling window because this error has engulfed it. And we talked about this as being something, so this is an example from Canada up north where this issue is more common. But if you look at this event in Texas, so we don't necessarily have an observatory in Texas, but we have one, Tucson, Arizona, Stennis Space Center in Louisiana, you can see 0.5 degree sustained shifts for the period of this storm. And if you're seeing the same effect in both Arizona and Mississippi, you can feel pretty confident something similar was happening in Texas. So if you were drilling overnight on the 10th, on the 11th, there might have been this 0.5 degree shift if you weren't compensating for it, if you didn't resurvey, if you weren't taking precautionary actions.
And you bring that up, Mark, and that's great because in Texas, in the Permian, we had an operator that was drilling during this event. And they were using a survey management company, one of our competitors, and the surveys were being corrected, which and it's important to say that they should not be, right? That this is something that cannot be corrected. This is something that can only be monitored. And they were being corrected, the operator ended up having to run a gyro because the surveys, they just didn't trust them. And they were actually over 150 feet off at bottom hole. And they completely missed their target. And it's important to know that you cannot correct for this error other than using certain tools. Algorithms like multi-station analysis cannot fix this error. And Mark, maybe you can go a little deeper into that, but it's important to know that multi-station analysis algorithms cannot fix this error.
Well, and touching to Mark on, okay, we know what can't fix it. What can you do?
Yeah, so active monitoring. So it is literally collecting extra data. And, again, I say this as someone who's a bit of technical advisor on the technical side. Like, you should always be hungry for data. Data is a great thing. So I was traveling over the weekend, for the holidays. This is being filmed after the 4th of July. I was stuck in the airport for a bit because there was a weather causing a ground stop. If you're flying, if you're navigating, the weather is so important. Directional drilling is subterranean navigation, and space weather is our weather. You wouldn't want to get onto a plane where the pilot said, I don't need to check the weather. The weather's not important. We'll fix the weather with an algorithm. That's not really how it works. And so similarly, when you're drilling and you have to worry about space weather, you're doing magnetic surveying, you should be hungry for data. You should be concerned about the space weather. You shouldn't trust that you can fix it with fancy math, because this type of event violates most of the assumptions of a lot of those algorithms. And so their results could really go awry if you're not careful.
And Mark, can you bring up the Stennis Space Center in Tucson, Arizona map? Because I want to answer Ali's question, kind of the ways that we can, the data, how we get the data, or what type of data we can use to monitor a situation like this and actually correct for it. So there's two different ways. There's IFR2, or in-field reference 2. That is literally our own monitoring station that we put at the rig's location, and we monitor for what we call diurnal effects, or daily solar events, right? And it gives us all the data we need, and we're able to take that data and correct for something like a solar event. There's also double IFR, and I wanted to use this map because you have this Stennis Space Center monitoring station, and you have this Tucson monitoring station, and what we call interpolated in-field reference. So you're going to interpolate a value between these two states, monitoring stations, and it'll give us, like Marc was saying, like half a degree or whatever it was in between these two. So the more data we have, the better it is that we can correct for this. And that's the only way that that we can correct for a solar event like this. So like we were saying, an algorithm-based like multi-station analysis won't do it. You have to do something extra to get more data to understand what's happening, and then we can make the correction.
So if you have a survey management provider, someone who's doing your survey management, what would you tell operators listening to ask that provider when it relates to solar storms to make sure that this is being covered?
So for me, the question that I believe needs to be asked is, how do you handle this situation? Because we know that it's going to be something that's going to happen a lot more in the near future because of the whole solar maximum, right? So the question should be, how do you handle it? And the answer should be what we're talking about here, double IFR or IFR2. If someone should say algorithm-based solution, it's not right. It's not the right thing to do. Marc?
Yeah, and IFR2, collecting additional data, great option. There are also other workflows where if you work with your survey management provider as a trusted advisor, there are potential options that can work. For instance, Paul was talking about some of our customers out in the Permian. If you know the solar storm is happening and you know that those surveys might have additional error, it might work out for your operation where if you can plan it, you say, hey, we're not at a critical point of the well. We're not at a collision avoidance part of the well. We're not the half a degree isn't critical. We can reshoot these surveys when we trip in. We can take check shots to verify, did we see an error? There can be ways to plan out with a trusted advisor how to manage this situation. The most straightforward, most accurate, least painful operationally would be to just collect data, run IFR2. But there are ways to juggle your operations and say, if I'm willing to reshoot surveys, if I'm willing to do check shots, if I'm willing to pull back and collect data mid-run, there are other ways to mitigate it. It's just often those are undesirable to say, hey, we're going to need to stop drilling, do a short trip and reshoot surveys, or hey, we're going to have to fill pipe and shoot surveys again on the way out of hole. Sometimes that's not what folks want to do because it takes time, it takes effort. You have to communicate across towers potentially.
But yeah, Ali, the question that she needs to be asked to any operator, or the question that needs to be provided to the operator to ask their survey management company is, how do you handle a solar event? Like, that's the only question that there is, and the answer should be straightforward.
Yeah, there's no one specific right way to deal with space weather, but there's a lot of wrong ways. And if you're not handling it, then that's a wrong way.
I appreciate the extra context there. And I know that you might have mentioned it at the beginning. How long is this going on? A few months thing, a few years thing?
Yeah. Go ahead, Paul.
But, okay.
It's an 11-year cycle.
It is an 11-year cycle, and it is going to be on the upswing for the next, say, year to year and a half. Then we're going to start seeing it kind of decline. But we're going to see some pretty significant storms here. And, Marc mentioned one in June. We saw a G4 storm, and I was actually in Canada meeting with operators as it was happening. And it was good to see. It was good to talk to the operators. And there was one Canadian survey management provider who decided that corrections were the right way to go, and it caused some issues. But yeah, it's an 11-year cycle. We're on an upswing right now. We're going to start seeing a downward trend, and by 2030, we'll be hitting into the kind of solar minimum, and then it'll just kind of recycle after 11 years.
Marc, did you have anything to add?
Paul said it right. So there's going to be potentially another year to year and a half of increasing volatility, and then we'll come out of it. So in maybe 3 to 4 years, we'll be at the same place we are now of potentially still very large events. And then it'll be a calm period. And that's also why, depending on how long you've been in wellbore positioning, how long you've been doing directional drilling and directional surveying, you might not have heard as much about this in the US, is because for the last 6 to 8 years, it hasn't been a big issue. We've been in a minimum.
Mm-hmm.
And even then, like this graph shows, the previous solar peak was relatively mild compared to historical ones. So there's a chance that this is a phenomenon that has not impacted your career to this point, even if you're in a fairly senior role.
That is a good, yeah, that's interesting. I know we have kind of come up on our time. We're trying not to go too far in the weeds on this, but closing this out for you guys, what is the bottom line on top? What's the one thing for anybody who's stuck with us through this that you want them to leave knowing?
Mark, you go first.
Yeah, I think to come back to how you kind of kicked us off, Allie, the idea that we're entering a solar hurricane season and that this directly impacts your navigation, just as if you were flying a plane out of Houston in the last couple of days.
For me, it's important that directional companies especially understand that this can affect their surveys. It's important for operators to know that when drilling during a solar event, that they may not hit their target. And questions need to be asked to directional companies, survey management providers. How do you handle the situation? What do you do? What can you do? And I think once that is spread around all directional companies, this particular error will be easier to mitigate and easier for the operator to understand.
And actually, one last important point to tack on to what Paul was saying about the missed targets and things like that. It's not just that there's a risk of missing it. You won't know you missed it until there's an adverse event. So you won't know when you drilled this well that you drilled it 75 feet off. It's when you're drilling the next well and you have an unexpected near miss on collision avoidance and you say, why is that well 75 feet away from where I thought it was?
Or you're drilling this well during a solar event and you don't understand why you hit another well when you should have been, 50 feet or 60 feet or 100 feet away, but you ended up colliding with another well because your surveys are so off. So it is important to realize that can happen.
I mean, that's catastrophic when that happens.
It is. Yeah.
Yeah.
And it was for one operator. Just remember, the one operator in the Permian, they were 150 feet off. They had to redrill the whole well. So it was pretty catastrophic for them.
What do you think that cost?
So redrilling an entire well, $2-3 million.
Wow.
Or more.
That's an expensive mistake.
Yes, it was a very expensive mistake.
Okay, well, thank you guys so much for coming on, talking through this. I'll close this out for today. If anyone listening wants more information, visit our website. We have some other resources that could be relevant for you. We also have our chatbot on the website. We like to call him Derek. And on the other side of Derek, there's real people. So if you want to chat with someone, set up a meeting with our survey management team, they'd be happy to get you connected. We make it pretty easy. So with that, thank you everyone for joining and have a great rest of your day.
Thanks so much, Allie.